Among the hundreds of moons in our solar system, one stands apart. Titan is larger than the planet Mercury. But size is not what makes Titan extraordinary. Titan is the only moon with a dense atmosphere. That atmosphere is thick with nitrogen, similar to Earth. Yet temperatures are extreme. Surface temperatures average around -179 degrees Celsius. At these temperatures, water behaves like rock. But something else behaves like water: methane. On Titan, methane forms clouds. It rains from the sky, it flows through rivers, and it collects in lakes and seas. This makes Titan the only world besides Earth known to host stable liquids on its surface. But those liquids are not water. They are hydrocarbons. When the Cassini-Huygens spacecraft studied Titan, it revealed something astonishing. Radar imaging penetrated Titan's thick haze. Underneath were landscapes carved by flowing liquids. River channels stretch for hundreds of kilometers. Some flow into enormous methane seas. The largest sea, Kraken Mare, spans an area larger than the Caspian Sea on Earth. Rainstorms shape the landscape. Seasonal cycles move methane through atmosphere, surface, and lakes. It is a hydrological cycle. But instead of water, the working fluid is methane and ethane. Titan has weather. Titan has seasons. Titan has erosion. In many ways, Titan behaves like a frozen mirror of early Earth. Titan's atmosphere is rich in organic molecules. Sunlight and Saturn's magnetosphere drive chemical reactions high in the atmosphere. These reactions produce complex hydrocarbons. Particles fall slowly through the atmosphere like organic snow. Over time, they accumulate on the surface. Scientists suspect Titan's chemistry resembles conditions on early Earth before life emerged. Organic molecules mix with liquid methane lakes and icy crust. This combination creates a natural laboratory for studying prebiotic chemistry. Titan may not host life today, but it may reveal how life begins. Titan combines three critical ingredients for complex chemistry: an atmosphere, organic molecules, and stable liquids. But studying Titan from orbit is not enough. The most interesting chemistry happens on the surface. To understand Titan's chemistry, scientists need to move across its terrain. They need mobility. They need sampling. They need a laboratory. That requirement led to an extraordinary idea. Instead of a rover, send a flying machine. The mission that will do this is called Dragonfly. On Earth, flying requires powerful engines and large wings. Air is thin and gravity pulls strongly downward. Titan is different. Its gravity is only about 1/7 of Earth's. At the same time, Titan's atmosphere is 4 times denser than Earth's. This combination changes everything. Low gravity means objects weigh less. Dense air means rotors generate lift more easily. In fact, Titan may be one of the easiest places in the solar system to fly. A human with wings could theoretically glide across Titan's skies. For engineers designing an exploration vehicle, this environment creates an opportunity. Instead of driving across terrain slowly like a rover, a spacecraft can fly from site to site. The atmosphere that once made Titan difficult to observe now becomes an advantage. Dragonfly will use this environment to explore large regions of Titan's surface. Each flight will cover several kilometers. Over its mission lifetime, Dragonfly could travel hundreds of kilometers. This mobility transforms planetary exploration. Dragonfly will operate far from the Sun. At Saturn's distance, sunlight is weak. Solar panels would not provide enough power. Instead, Dragonfly will use a radioisotope thermoelectric generator, an RTG. This system converts heat from radioactive decay into electricity. RTGs have powered several deep space missions. Examples include the Mars Curiosity rover and the Voyager spacecraft. But Dragonfly will use this power in a new way. The RTG will charge onboard batteries. Those batteries will power the rotors during flight. After each flight, Dragonfly will land and recharge. This cycle allows repeated exploration hops across Titan's surface. Energy independence is critical. Titan's long nights and thick atmosphere make solar power unreliable. Nuclear power ensures the mission can continue for years. Dragonfly looks like a large drone. It has 8 rotors arranged in 4 pairs. This configuration provides redundancy and stability. If one rotor fails, the spacecraft can still maintain controlled flight. The vehicle weighs about 450 kilograms on Earth. But on Titan, its effective weight is far lower. This makes powered flight feasible with moderate energy. Dragonfly also carries scientific instruments, mass spectrometers to analyze organic molecules, gamma ray and neutron spectrometers to measure surface composition, meteorological sensors to study Titan's atmosphere, cameras for geological mapping. Together, these instruments transform the rotorcraft into a mobile chemistry laboratory. Instead of analyzing one landing site, Dragonfly will explore many. Each flight reveals new terrain. Each landing becomes a new experiment. Dragonfly's landing region lies in a vast equatorial dune field called Shangri-La. These dunes are composed of organic particles created in Titan's atmosphere. Between dunes lie areas where water ice bedrock may be exposed. Scientists suspect that occasional impacts melt subsurface ice. When liquid water mixes with Titan's organic chemistry, complex reactions could occur. These locations may contain clues about prebiotic chemistry. Dragonfly will investigate these environments directly. Each landing site offers a new sample. Each flight expands the map. For the first time, a spacecraft will roam across an alien world not by wheels, but by wings. Titan's atmosphere functions like a giant chemical reactor. High above the surface, ultraviolet radiation from the sun interacts with methane and nitrogen molecules. These reactions produce complex hydrocarbons. Over time, those molecules combine into larger organic compounds. Some resemble the building blocks used in biological chemistry. Particles formed in the upper atmosphere slowly drift downward. They accumulate across Titan's surface like a thin organic snow. This continuous production of organic material has been occurring for millions of years. On Earth, organic chemistry eventually led to biology. On Titan, similar chemistry occurs in a completely different environment. The temperature is extremely cold. Liquid methane replaces water. Yet the raw ingredients for complex chemistry exist. Dragonfly's mission is to investigate whether these reactions create molecules similar to those that preceded life on Earth. Dragonfly is not just an explorer. It is a mobile laboratory. Once landed, the spacecraft will drill into Titan's surface. Collected samples will be analyzed using onboard instruments. The mass spectrometer will measure molecular composition. It can detect complex organic molecules, including potential precursors to amino acids. Dragonfly will also measure isotopic ratios. These ratios help scientists understand how Titan's chemistry evolved. Because the spacecraft can relocate, it will compare samples from multiple locations. Some areas may contain freshly deposited atmospheric particles. Others may expose ancient materials buried beneath dunes. By studying variations across sites, scientists can reconstruct Titan's chemical history. Each landing site becomes a new chemical experiment. Titan's surface is mostly frozen, but impacts from meteorites occasionally melt subsurface ice. For a brief period, liquid water may mix with Titan's organic compounds. Water is chemically reactive. When combined with organics, it can accelerate complex reactions. Some scientists believe that these temporary environments may allow prebiotic chemistry similar to that which occurred on early Earth. Dragonfly will investigate impact craters where such mixing may have occurred. If chemical complexity increases near these locations, it may reveal pathways toward biological molecules. The spacecraft will search for patterns in molecular complexity. These patterns may tell us whether Titan's chemistry is simply random or evolving toward something more organized. Dragonfly is not designed to find living organisms. Titan's extreme cold likely prevents active biology. But the mission may answer a deeper question. How does chemistry become biology? Life on Earth likely emerged through a gradual progression of molecular complexity. Titan preserves a world where similar chemistry occurs without life interfering. It is a natural laboratory for studying prebiotic processes. If Dragonfly discovers complex organic chemistry forming naturally on Titan, it could reveal how early Earth chemistry evolved toward biology. Understanding Titan may therefore help explain our own origins. A flying robot exploring a distant moon could reveal the chemical story that eventually led to life on Earth.